Let us practice the line integral using this following exercise. We want to compute the curve integral of the vector field f dr along the curve C, where C is given by these two parametric equations. X is t and y is t squared, where the parameter t runs from the interval -1, 1. And the integrated vector field at the point xy has the components 2xy and x. Note that this notation is valid independently of the dimension. In the previous exercise, this was a three-dimensional problem. The vector field and the position were three-component vectors in a three-dimensional space. We integrated along a segment in a three-dimensional space. And this dot stands for the dot product, which was the dot product of two three-dimensional vectors in the previous exercise. And here, the same notation can be used to describe a two-dimensional problem. We have two coordinates in a plane. We have a vector field in a plane which assigns to each point this vector, this result. Two inputs, two outputs. And we have two variables as a function of the parameter t. So we prepare the derivatives or the differential. dx is dt and dy is 2t dt. Well, and we have all we need to evaluate the integral. We will write each expression as a function of t, and t runs from -1 to 1, and this is f1 dx plus f2 dy. f1 is equal to 2xy, x is t, y is t squared, times dx, which is dt. We will write dt at the very end. Plus f2 is x, and x is t, times dy, and dy is 2t. And we are done. We have successfully converted the line integral into a definite integral of one function of one variable. Okay, we can compute this. T cubed is an odd function. When integrated over a symmetrical interval, gives 0. And this is 2t squared. So the antiderivative is 2/3 t cubed. And we can consider the integral from 0 to 1 and multiply by 2, because the integrated function, this term, is an even function. Evaluated at 1 gives 4/3. Evaluated at 0 gives 0. So this is the result of this line integral.